Okay, so section 2.1 is what we're looking at, and we're going to be looking at tangent, which, like a tangent line, that's going to be like the heart of Calc 1, really. And then you'll see Calc 2 later. We'll be doing other things that are kind of like the opposite of Calc 1, but we'll get to that. So in Calc 1, we're interested in finding slopes of what we call tangent lines, and we'll talk about what that is. So the word tangent is actually derived from the Latin word tangens, which means to touch or touching. Okay, so the idea is that a tangent line to a curve is a line that touches the curve. And then a secant line, the word secant, is derived from the word, Latin word secare. I don't know if I'm pronouncing it right or not. And that means to cut. So just the meaning of those two words, you can kind of get an idea of what the difference is between these two lines. A secant line will cut, and a tangent line will touch. Okay, so let's go ahead and get some practice with drawing secant lines and tangent lines. Let's actually start with drawing a dotted secant line through the point C and D. So I think maybe I'll do that with a red line here. So I'm going to do dotted secant line. I'm just going to underline it so I know which one I'm using. So a dotted secant line through C and D. Now this might be a good point to take out like a straight edge of some kind, just so that you can get some precision. Your student IDs work really well for this, so if you don't actually have a straight edge, just take out your student ID, and it works. All right, so let's go ahead and continue looking at this together. Okay, so what did you guys get for the second part between 1 and 2? 0, right, because the rise is 0, there's no rise, and then the run, you could say, I guess, is 1, but it doesn't really matter what you say the run is, because 0 divided by anything other than 0, we'll talk about that, is 0, so slope of 0. Okay, between 2 and 3. Yeah, 0.75, and in this class we'll generally like to deal with fractions instead of decimals. You're totally right, 0.75. I'm going to say 3/4 because we go over 4. Well, really we go over 1, don't we? Yeah, we go over 1 and we go up 3/4. But since the scaling is the same, do you see how it would be the same as if I did go over 4 and up 3? Right, because the tick marks on the x-axis are the same as the tick marks on the y-axis. So you'll get the same thing in this particular case. So 3/4, and then with this one, I go down 1/4 over 1. So slope then of -1/4. This one looks like a slope of 3/4 again, doesn't it? Goes over 1, up 3/4. Yep. And this one looks like our same 1/4 here, it's just not negative. Goes over 1, up 1/4. Okay, 0. And then this one is nice and steep. Now, you can kind of, when you go through this one, I would just generally look and see when a next somewhat nice point is. You see how the last one's a little bit harder? It doesn't seem to go through one distinct nice point. It almost seems like it goes through here, but then do you see how it doesn't go through that point? So it almost looks like 1/2, but it's not. I would maybe go over to, seems like it's going to be roughly through that point there. So I'd go maybe through there. This is just eyeballing, right? We might not be 100% precise, but so I go over, and I go over 1, and then up. This would be 1 3/4. And I also don't like mixed fractions. We're not going to do mixed fractions much in this class, so like 1 3/4 would be a mixed fraction. Improper fractions are a better way to go, so that would be 7/4. And you can also calculate that by going over 4 and up 7. That would be 7/4. Okay, how are we feeling about eyeballing slope? Pretty good? Okay, so let's move on then. So finding the slope of a secant line is really easy, which is kind of what we just found because we had kind of two distinct points, because it crosses and it goes through 2 points. And slope is defined as rise over run, where it's a difference between the 2 different points, right? So it's a little bit more difficult to find the slope of a tangent line because it just touches the curve, and so that means it goes through 1 point instead of going through 2 points. So we can find a few different ways to approximate the slope of a tangent line, one of which is we can just draw the tangent line and then approximate the slope, just like what we did here, right? Draw a tangent line, which is what we did in this circle part, and then we just learned how to just approximate the slope by eyeballing a line. So kind of bringing those two ideas together. Another way is we can do it numerically. That is, we can find, we can use a second point. Instead of just 1 point, let's pick some other point that's on the curve. make a secant line, and then try to get those 2 points as close to each other as possible. That one might not seem super intuitive, but you'll see as we keep going why that's going to be a good approach for us to take. And then you can also find it symbolically, which it uses what we call the derivative. Who's heard of the derivative in calculus? That's the thing. It's like if you talk to someone about calculus, they'll go, oh, it's about derivatives and stuff. So we'll talk about derivatives a lot, but we're not quite there yet. It'll be down the line. But I wanted to show you that there is a silver lining. There's a light at the end of the tunnel. We're going to do it the hard way, and then we'll find a slightly easier way of doing it. So, all right, let's do an example. So let's consider the function x squared minus 4, and we're going to try to approximate the slope of the tangent line at the point 1, -3. And we're going to do this in 2 different ways. We're going to do it graphically, and we're going to do it numerically. So graphically, we're just going to try to draw our best tangent line at that point, and then try to approximate the slope. Okay, so you guys go ahead and give it a try based on what we did in that first page. Try to draw a tangent line at this point, 1, -3. Try to use a straight edge if you can, and then approximate the slope. Will you guys maybe get slightly different answers on this? Yeah, you know, you and the person next to you probably aren't going to draw exactly identical tangent lines. It's possible, but so I want you to do that and then talk with someone next to you and see if you're getting at least roughly similar slopes. All right, so what are we roughly getting? Let me just shout out what you're getting. About 2. I think I heard some fractions too as I was walking around, like 12/7 for being super precise. Right, so it looks like we're looking at numbers fairly close to 2. Okay. So I'm going to go ahead and draw mine and kind of see how I'm looking as far as slope goes. I feel really funny holding a ruler up to a screen. Am I the only one that seems like it feels a little silly, doesn't it? Oops, especially when you accidentally hit something. Oh, that looks pretty good. Oh, there's my best attempt at a tangent line. Okay, so now the tricky part is you have a line, right? And you're trying to find the slope. How many points do I have on this line right now? Just 1. So you just need to find some other point. The point that you find might find the slope might be different than the person next to you, and that's fine. I will generally just kind of hunt through and see. It looks like maybe this point right here is roughly kind of going through a nice grid where the grid intersects. So I'm going to pick that one. And then it appears that I go over. Now using the proper scaling, this length is what? Half, and then the height is 1. So using the proper scaling, I have rise of 1 over a half. So slope would be 1 over a half, which is 2. So I'm getting about 2 for the slope. And like I said, the scaling's the same, so you could have done over 2 up 4, which also would have had a slope of 2. Okay, how are we feeling about that? Now, does this seem like a very precise technique? Not so much, but it's an intuitive technique, isn't it? Just kind of drawing it and like, oh, what does it look like? Okay, it looks like about 2. All right, but I think we can do better. We can do a better technique for finding a more precise slope. So the way that is going to happen is numerically. What we're going to do is we're going to choose a second point. Because you guys agree it's easy to find the slope between 2 points? Super easy. You got your 2 points, rise over run, no problem. So we're going to pick a second point. And I think I'll make that red. And here's our second points. So we have x1. That one's going to always be at 1. That one's not going anywhere. That's what I like to call my stationary point. But then we have x2, where we're going to change the location of x2 to try to make the secant line become closer and closer to a tangent line. So the idea is with our first one, we're letting x2 be 2, which means that we would have the point x equals 2, which is right here. Now, if I connect those 2 points, that is this point and that point, that would be a secant line. Let's do that. I think I'm going to make it smaller. It's easier to draw a more precise line when it's not so zoomed in. Now, how close is that to the actual tangent line? It's a start. We can do better, but it's a start, right? Is it steeper or less steep than the actual tangent line itself? It's steeper, and if I calculate the slope just kind of using the rise over run idea, I can see that I go over 1, and I go up 1, 2, 3. So currently the slope is 3. I can actually write that down here. But let's actually figure out how we would find that numerically instead of just eyeballing it, because if I want to go between 1 and 1.0001, it's going to be very hard for me to eyeball what that slope is. So we're going to need kind of the numerical approach to it. Okay, so the slope between 1 and 2. Okay, the idea is that I want to take the change in y over the change in x, right? So essentially what I want to do is I want to take the change in the outputs and divide it by the change in the inputs. The change in the outputs is going to be based on this function right here, right? That function gives me the y values. So notice that if I plug 1 into that function, what do I end up getting? 1 squared minus 4, negative 3. That's the point, right? Right there. Okay, so that's going to give me the y values. So I want to find the change in the y values, which would be taking f of one output, subtracting f of one input and subtracting f of the other input. So f of 2 minus f of 1, that's my change in y. My change in x is 2 minus 1. I'm using this idea up here, right? This idea of slope. Slope is the change in y over change in x. It's the subtraction of y values divided by the subtraction of x values. I can represent the y values using my function notation because the function gives the y values. So there we go. Now I can just plug in f of 2 to figure out what that y value is. Okay, well my function is 2 squared minus, or x squared minus 4, so 2 would give me 0. So I'd have 0 minus f of 1 was negative 3. 2 minus 1 is 1. Okay, 0 minus negative 3. There's our 3. But now I've calculated that slope in a more numerical approach instead of looking at the graph. Feeling okay so far? Questions? I just said that in a really high-pitched voice. Questions? No? Okay. All right, let's get the point closer. As we said, it's an okay start, but it's not great. Let's get it closer. Let's try going to 1.5. I don't think I'm going to draw it just because it gets to a point where you've got so many things going on that it becomes unhelpful, but I'll show you a Desmos applet where you can really see that point coming in. Okay, so 1.5. We again want to take the change in the outputs minus, or divided by the change in the inputs. Now I could, by hand, calculate f of 1.5. 1.5 squared would be 2.25 because 15 squared is 225. Minus 1 would be 1.25 divided by, I could do it in my head, but it's going to get harder and harder to do that as we go forward. So let's employ some help. That could be your actual calculator if you have one. I'm going to use Desmos because I love Desmos. And I'll show you some tips and tricks that you can do with Desmos to make your life much easier. Okay, so to go to Desmos, it's just desmos.com. If you're feeling super comfortable with your graphing calculator and that was the first thing you reached for, that is perfectly fine. But what you might want to also do is actually go to Desmos with me, if you've never been there before, and try out some things on here. So I think what I'm going to do first, I'm going to go to the graphing calculator. And you'll see here we have a nice free online graphing calculator. So what I was trying to find was f of 1.5 minus f of 1 over 1.5 minus 1. So I can show you a few different ways that we can do this. One way is I can actually plug in 1.5. That is, okay, I'm going to hit my division bar, but you can also, you can use your keyboard or you can use the little pop-up keyboard here if you feel more comfortable with more of a point and click kind of menu option. So I have my division. Where's my division? I almost never use this one. I guess I can just do that. There we go. It creates a fraction for me. I want to plug in 1.5 to the function. So remember that the function was x squared minus 4, right? Actually, let me do this just to remind us. The function is x squared minus 4. So I just did f of x equals x squared. Remember to use a caret to do an exponent, or you can use the exponent command down here. So the function is x squared minus 4. Notice I have a nice graph of it. Thank you, Desmos. So I'll do it again. Okay, so you just type in f of x equals, and then you can either do this command. Well, you would want to do the x first. x squared minus 4. Are you still in a fraction, maybe, Keith? That's what Josh is saying. Yeah. So I'm just typing in the function right now. And then now we're going to actually go ahead and calculate that rate of change that we just found, the change in y over change in x. Okay, so we wanted f of 1.5, which would be 1.5 squared minus 4. We want to subtract f of 1. F of 1 was negative 3. Oops. And then we want to divide that whole thing. So if you highlight the whole thing, you can then hit divide, or you can use your keyboard to hit the backslash. I'll do this one since you can see it. You could also have done that first to create the fraction and then type it in the numerator and type it in the denominator. And then I want to divide by 1.5 minus 1, right? That's my slope, by change in y over change in x. And let me show you if I had done 2 squared minus 4 minus negative 3 divided by 2 minus 1. That was the first one that we calculated, right? Notice that it's giving me an output of 3. I'm going to actually make this come first. Okay, there's the output of 3. So now I've done 2, I've done 1.5. Okay, well, so what was the result? 2.5. So I'm going to come in and write that down. Whoops. I might have to reconnect. It does that sometimes. Back up. Okay. So rather than doing this part by hand, I'm going to, okay, Desmos, do the work for me. I got 2.5. Does it make sense that we got a smaller value than 3? Because as I move that point in, I was at 1.5, which is here. I now have a less steep slope, and notice that that line, if I were to connect those two, that line is now closer to the tangent line than the one from 1 to 2. Okay? All right, let's do 1.1. Now, you might be going, oh, this is really tedious. And yes, it is. But there are some things that we can do to make this process easier on ourselves. One way is if you're using Desmos, you can copy and paste because it's on a computer. So I'm going to take this, copy it, paste it, and then now what do I want to do to edit it, to make it the next one? Change the 1.5 to a 1.1. Now I need to do that in both the numerator and the denominator, right? There we go. Changed it to 1.1. Okay, I got 2.1 as a result. Hey, now it's closer and closer to the 2 that we were kind of finding when we drew the line. So I get 2.1 now. I'm not even going to really bother with writing it down here. Actually, I think I will just this one time. This was f of 1.1 minus f of 1, 1.1 minus 1. Now I can do 1.01. You see how we're getting closer and closer to that 1 value? 1.01. And I need to change the denominator too. And I get 2.01 as a result. Okay, now I need another 0. Now I get 2.001. If I were to add another 0 and do 1.0001, what do you think the result would be, based on what you're seeing so far? 2.0001. Be another 0 there. Now, I have a question for you guys. Is there any limit on how close I can get that second point to 1? I can always add more zeros, right? 1.00001. Can always do more, right? Which is why I like to use the word limit. Exactly. You can't ever actually get to that point 1. But here's the thing. Do we actually want that second point to be exactly at 1? Let's think about that. If that second point was exactly at 1, my slope would be f of 1 minus f of 1 over 1 minus 1. What's the numerator? What's the denominator? Ugh. That doesn't tell me anything, does it? Now, you might be tempted to say that 0 divided by 0 is 1, because any number divided by itself is 2 divided by 2 is 1, 7 divided by 7 is 1, right? It doesn't work for 0, though. And there's a great analogy where Siri, if you ask Siri on your phone, if you have an iPhone, what is 0 divided by 0? She says something along the lines of, imagine you had 0 cookies. No, what is it? Imagine you had 0 cookies and you wanted to divide it up between 0 friends. See, it doesn't make sense. And now Cookie Monster is sad because there's no cookies and you're sad because you have no friends. That's what she says. It's pretty funny. All right, so this is what we call indeterminate form, and we are going to be exploring this a lot in both Calc 1 and Calc 2. The reason why it's called indeterminate is I can't determine what it is. That is, 0 over 0 has no value. There's no value to 0 over 0. It is indeterminate. So anytime you get a situation like that, but the idea is that we don't want the 2 points to be the same anyway, right? Because to find the slope between 2 points, we need 2 points. If I have just one, it doesn't work out. I need 2. So the idea is we pick a second point, we get it closer and closer and closer and closer and closer to the other point, but we don't ever want it to actually be the same as the other point. We just want it to get as close to it as possible. Okay, let's keep going with this idea. Now with in Desmos here, this isn't too hard to compute, right? Doing this copy paste, adding more zeros, it's not terrible, but there's an easier way. Are you noticing that what we're doing is we're just changing this number and we're changing this number, right? So let's create a new function that has an input in those spots. That is, we're going to take the function, we're going to take f of x minus f of 1 and divide by x minus 1, right? Notice that the things that we were plugging in, oops, I wanted that to be green, right? That's where we were plugging in, f of 2, 2, right? Those were the numbers that we're changing. So we're going to now call that x. We're going to make it some input instead. Does it have to be x? No. You could call it x2 if you wanted to make it more like how we, maybe I'll just do that actually because we did call it x2 here, didn't we? So whatever f of x sub 2 is, okay, so that's the number that's changing. So here in Desmos, what we can do is we can make a table. And that's going to really help us to see these slopes a little better, just like the table that we're constructing right now in our notes. I clicked on, great question. I know, I kind of tend to move kind of fast. So if you're in here, you go up to the plus button, and then you select table, and it will insert a table for you. Okay, now I'm going to change this to x2 instead of x1, because x1 is like my stationary point, and x2 is my moving point. x2. And then in my y column here, I would like this to spit out the slope between x1 and x2. So the way that we found that, right, was this. We want to take f of x2. Now to do the subscript, you can actually just type 2, and it just kind of, it reads your mind, and it knows that you want it to be a subscript. You can also do the subscript button somewhere around here, but you don't have to. Minus f of 1. Now I want to take that whole thing and divide by x2 minus 1. Now here's the thing. It knows what f is because I defined f being x squared minus 4 up here. So if you didn't do that, Desmos would go, I don't know what you want f to be. You need to tell me. So if you haven't defined f of x equals x squared minus 4 yet, make sure you do that before you construct your table. Okay, so now here are some things that I would like to plug in. So whatever I type into here, Desmos is going to plug it into f of x2 minus f of x1 over x2 minus x1. 2, what'd I get? 3, which is the same thing that I got earlier. Okay, 1.5, 2.5. Oh, notice what it says when 1 goes in. What does it say? I don't know if you can see it very well. It's kind of, let me come down here and add some more so that it goes up a little bit. Undefined, because it's 0 over 0. Good job, Desmos. 1.1, 1.01, 1.001. And do you see how now it's extremely easy for me to do any number I want to here with minimal effort? I can add as many zeros as I want here. You can even just keep adding zeros. Now here's the thing, it says 2, but it's just gotten so close to 2 that it's rounded to 2. It's really not 2. Notice if I take away some zeros here, there we go. It's just adding another 0 every time I add another 0. So now notice that what that's doing is that's taking a look at these points that are approaching 1 from the right side. That is, numbers that are bigger than 1 are being plugged in. But it's a good idea to go ahead and go in from the other side too, just to make sure that you're looking at like both pictures of what's happening here. So we're also going to look at plugging in 0.999. Let me see, where's my red one here? So 0.999, 0.999, and it's just going to nicely do that for us. And notice that we get 1.999, which is a slope that's just smaller than 2. So we're kind of going, we're kind of wiggling in between that tangent line there. And we can do 0.99, 0.9, and we're basically just kind of repeating what we had done in the other one. I'm actually going to get rid of this one here. Oh, maybe it won't let me. Oh, there we go. Okay, I'm just making it so it matches the table that we have. What did I do here? 0.5, I think, and then 0. Right? Okay, so there's our table, and notice that the input is the second point that I'm picking along the curve, and the output is the slope of the secant line between those 2 points. Okay, I'm going to fill in the rest of my table here. It was 1.999, 1.99, 1.9. This one was 1.5, and this one was 1. Okay, so remember what I said earlier, there's no limit on how close we can get that second point to the other point, right? But as it gets closer and closer, what does it seem like the slopes are approaching? Seems like they're approaching 2, doesn't it? Because if I add another 0 here, I just add another 0 here, right? It just keeps getting closer and closer. So it seems like the slope of the tangent line is 2, because that's what the slope of the secant line is approaching as I'm getting those 2 points closer and closer to each other. Does this technique seem more accurate than just drawing it and eyeballing it? Definitely, because you're actually using the function to get precise y values instead of just letting your eyes figure out what the y value looks like. So it's much more precise. And so it seems like the slope is 2. And now let's actually find the equation of the tangent line. Now you might be thinking, we already did that. We found the slope of the tangent line, right? That's just one particular characteristic of the tangent line. But now I want to find the equation of the tangent line. That is, if I were to actually type in the equation, it would draw the tangent line for me, right? Notice if I were to go into Desmos and just type in the slope, 2, it doesn't do anything. So that doesn't help me. So what we want to do is find the actual equation of the tangent line. There's a few ways you can do that. You've probably heard of slope-intercept form, y equals mx plus b. I don't recommend using that one because then you have to solve for what b is, and it's a whole process. Instead, I like point-slope form because it's exactly what we have. We have a point, we have a slope, we don't have an intercept, right? And we're never going to be given an intercept when it comes to tangent lines. We're going to be given a point, and we're going to find a slope. So point-slope form is y minus the y coordinate equals the slope times x minus the x coordinate. You're just going to want to remember this, but it's pretty intuitive because if you were to divide both sides by x minus x1, what you would end up getting is y minus y1 over x minus x1 equals m. Does that look familiar? That's slope. It just comes right from that. So then this is more of a plug and chug idea. You don't have to do any solving. What is the y coordinate at the point 1? Because that's where we're finding the tangent line at 1, -3. So -3. The slope I found to be 2, and the x-coordinate was 1. You might be very tempted, well, I probably would go ahead and at least do y plus 3 equals 2, x minus 1. I would just leave it there, though. I wouldn't even really bother solving for mx plus b. So what you can do from here is you can type this into Desmos. Get rid of all this other stuff. And this is the way that you're going to check your answer to see how good of a tangent line yours is. Y minus the y coordinate, which was y plus 3, equals the slope, which was 2, x minus 1. And you can change the color in Desmos if you're like, I want a red line instead. You just click and hold this little color part right here, and you can make it a different color. You can even make it dotted or dashed if you want to. I like to sometimes have my tangent lines dashed. Does that look like a good tangent line? Now, if I had gone through that process and maybe I got confused and thought that I was supposed to just find the y values instead of the slope, I would have gotten -3 as a result. Does that look like a tangent line? No. It goes through the point. That's a good start, but it definitely isn't tangent. It's not touching. I mean, I guess it cuts, right? Because it comes up here and it touches the curve up here as well. Okay, so I just want it to touch, and the only slope that'll make it do that is the slope of 2. Now, one thing that's pretty cool that I want to point out here is that when you have a slope, when you have a tangent line, so I'm going to do my point here, 1, -3, just so I have a point there. If you were to keep zooming in and zooming in on this point, you'll notice something interesting happening. What are you guys noticing? Yeah, we have two different things drawn. We have a curve, x squared minus 4, and we have a line. But as I zoom in, what's happening? They look the same, don't they? They look almost identical. That's another way you can think of a tangent line, is if you keep zooming and zooming and zooming in on a curve, it starts to look more and more linear. And we're just finding the slope of that line. Now notice that the slope, because it looks like a line now, doesn't it? The slope, if you do rise over run, it appears to be, well, 1, 2, right? It appears to be 2. Both the line, the dashed line, and the curve itself. Okay. All right, how are we feeling so far? Pretty good? Okay. All right, let's talk about some techniques. Now, maybe I will click on these actually. I put 2 links in here for you guys because I knew that you might not 100% follow that Desmos thing. So there's really 2 ways that you can find the slope of a tangent line using Desmos. So I have links here. This is the table way, which I just showed you. It's working on it. There it is. Okay, so this is basically what we just went through. And so the table, notice this is my f of x function. I have to define that. And then I'm going to choose x2. Now, this doesn't have to be x2. If you want this to be b, you just have, this would be b, and this would be b. It doesn't matter what that thing is, as long as it matches. As long as all 3 of those things match each other, you're golden. Okay, so I did x2. I'm going to go ahead and go back to x2. I'm just hitting the undo button. Okay. All right, so then notice what you can do is you can use that table and go, oh, okay, as that second point gets closer and closer to the first point, it appears that the slope, which is your other column, the slope appears to be approaching 2. So that's your kind of numerical way of approximating the slope of a tangent line. And then you can check by actually finding the tangent line, graphing it, and it should look good. You can even do that zooming in thing to kind of make sure that it doesn't ever deviate from what you expect. All right, you can also use sliders, which is kind of interesting. And I don't think I'll show you how to construct this, maybe on Thursday, but you can now use a slider and now actually see that point coming in closer and closer and closer. Ooh, what happened when I made them exactly the same? All's good. Oh. Line disappeared? Yeah, and it says undefined. Okay, they're the same. Okay, you're going to have a lab question about that, so I'm not going to go into exactly why. But so you can do a slider technique also, and you can also put in like actual values here. And notice it's giving you the slope right here. So this is a nice visual approach. You don't get the nice table to kind of see, but so 2 different ways that you can approximate that. All right, now let's talk about some different techniques that you can use to find the slopes of tangent lines, and like doing it numerically. And I want to try to generalize this a little bit. So you have some function f, and you're trying to find the slope of the tangent line at a point A, let's say. Now the numerical approach will always be that you pick some other point on that curve, and you find the slope of the secant line between those 2 points, but then you try to get the other point as close to that stationary point as possible. That will always be the numerical approach to finding the slope of a tangent line. But there's 2 different ways that we can do that. So if we go with this technique here, one way is you're finding a secant line between 2 points. There it is. Now this other point, I can really call this whatever I want to. It's the one that's going to move, so it makes sense to call it a variable, like x. So if I call this x, then the way that I find the slope is taking the change in y over the change in x. If my function's named f, what would be the y value at a? What could I call it in terms of the function? Be f of a. So this point is going to be f of a. And if x is my input, then the output is going to be f of x. So the slope is going to be the change in y, which is the subtraction of the outputs, divided by the change in x, which is the subtraction of the inputs. Now remember, the order matters. I wouldn't go f of x minus f of a over a minus x, right? You always want to make sure that you're going, whichever point you pick to be your like x2, it just needs to be consistent as you go through. So this would find you the slope of, would this be the slope of a secant line or a tangent line? This is the slope of a secant line. I'm going to go ahead and write m secant just to show this is the slope of a secant line between the points a and x. What would I do if I wanted this to more resemble a tangent line? Close. Do I want it to be exactly a? Right, if it's exactly a, we get the 0 over 0 issue. So I don't want x to necessarily equal a, but I want x to approach a. I want it to get as close to a as possible, but not actually equal it. So I want this point to kind of come in and get as close to a as I can. But it could also come from the other side, right? It could be over here, because x is my moving point. I can put it anywhere. If it was over here, I'd want it to move in and get closer and closer to a, but not actually equal to it. So as x approaches a, f of x minus f of a over x minus a will approach the slope of the tangent line, which I'm going to write as m subtangent. Okay, so the slope of the secant line, rise over run between 2 points. The slope of the tangent line is still the slope between 2 points, but I want those 2 points to get closer and closer and closer to each other. Now again, do you see why I'm not using equal signs here and I'm using an arrow? Right, I don't want them to be the same, I just want them to be as close to each other as possible. And we'll eventually find new notation for this that involves what we call limits. Okay, that's basically what we just did, right? Just in a more general idea. So let's take a look at another way that we can approach this, but using a slightly different variation. And that slightly different variation is, rather than calling this a variable, what we're going to do is call the distance between those 2 points, the horizontal distance, a variable. That is, I'm going to say, I'm going to add some number to a to get to that second point that I'm going to find the slope of the secant line between. And then the variable that we generally use for that is h. So we're going to say, let's let h be the distance between those 2 points. And do you see how that's really my change in x? That's really what my denominator is going to be when I end up finding the slope. Okay, so the slope of the secant line, well, let's see. If I take the number a and I add a length of h to it, what would this input now be? I heard it whispered in the back. A plus h, exactly. So I'd be taking a, whatever the number a is, and adding some length h to get to the next point. So that means that my output at a is still going to be f of a, right? But now my output at f of a plus, or sorry, at a plus h, I want to plug that into the f function to get the output. That would be f of a plus h. Now notice that adding h horizontally, is that the same as adding h vertically? No, right? It's going to end up being, if it was linear, if it was like a slope of 1 or something, then yeah, it would be the same. But most of the time, it's not going to be the same as just adding h to the output. But my slope then, the slope of a secant line, is going to be given by still the change in output over change in input. So f of a plus h minus f of a. That's my change in output. What's my change in input? H. Does this look familiar to anyone? Has anyone ever seen this before? Few people. This is called the difference quotient. Yeah, Doreen's seen it. The difference quotient. And it's really just another way to calculate slope. And you might be asking yourselves, why in the world would we need 2 ways to calculate slope? But the reason why is, well, there's several reasons why. Oh wait, let me finish my thought process here. Now with this one, this is a secant line, right? If we want this to approach a tangent line, let me draw my secant line in here. Oops. If we want this to approach a tangent line, I still want those 2 points to become closer and closer to one another. But now I have a new definition. I'm not using x, I'm using h. So if these 2 points are going to become closer and closer to one another, what is going to happen to that variable h? H is going to get smaller and smaller and smaller and smaller. The distance between those 2 points will become smaller and smaller. So h is going to approach 0. Now when h is positive, I'm coming into A from the right side, and when h is negative, I'm coming into A from the left side. That is, I'm subtracting some distance. I should do it this way. I'm subtracting some distance to have the point on the left side, and I'm adding some distance to get the point on the right side. So as h approaches 0, this difference quotient of f of a plus h minus f of a all over h will approach the slope of the tangent line. Okay. Again, notice I'm using arrows as opposed to equal signs, because notice if h is 0, what happens to the slope of the secant line? If that's 0, this would be f of a minus f of a, which would be 0, divided by, well, if h is 0, 0. I get 0 over 0 again. Okay, we're going to be talking more about that indeterminate form idea. Okay, so that's 2 ways of defining it. Now, again, you might be wondering why. Technique 1 is relatively more intuitive because it's just change in output, change in input, which is kind of how we tend to think about slope. The nice thing about technique 2 is that if you're going to do a table of values and look at this numerically, do you see how h is always approaching 0 no matter where your points are along any curve? Unlike technique 1, with technique 1, there's some a value and you want x to approach whatever that a value is. In the example we did, that a value was 1. But in the technique number 2, it doesn't really matter what a is. You're always going to want h to get smaller and smaller. So you have that consistency, which is kind of nice. So let me show you how we could do a table of values in Desmos using the second technique. Okay, so I'm going to go back to our kind of this one here. I already defined f, so you could again do a table. And now I'm going to make this h as my input, and this is going to be my difference quotient. So I did a division so that I could just type this in. F of, now a was 1, right? In the example that we did earlier, 1 plus h minus f of 1, all divided by h. And unfortunately, it kind of cuts it off a little bit, but I'll highlight it again so you can see. F of 1 plus h minus f of 1 all over h. And just as a little reminder, f of x is still x squared minus 4. Okay, so now I can plug in things for h. If I go back to my table here, I added this column here. These are your h values. This is how far away you are from that stationary point, whether you're on the right side of it or on the left side of it. So if your second point is at 2, that means you've gone 1 more away from 1, so your h value is 1. It's really just the subtraction of x2 and x1. So I want to plug in these numbers. 1, 0.5, 0.1, 0.01, 0.001, and then we'll do the other side, which notice if I do from the left, like 0.999, that is negative 0.001 units away. So negative 0.001, negative 0.01, negative 0.1, negative 0.5, and what was the other one? It would have been negative 1. So notice, you see how I'm getting the exact same results that we had gotten before? Three, 2.5, 2.1, 2.01, exactly the same. So now I can look at this and go, okay, as h gets smaller and smaller, the slope of the secant line between those 2 points gets closer and closer to 2, so I'm going to make an educated guess and say the slope of the tangent line appears to be 2. Same idea. The nice thing about doing it this way is that let's say now you want to find the slope of the tangent line at for a different function or at a different point. Let's stick with the same function. Let's say we wanted to find the slope of the tangent line at negative 1 over here. Now we already found the slope of the tangent line at this point was 2. Using symmetry, what should be the slope of the tangent line at this point? It should be negative 2, because notice it's the same slope except now it's negative slope instead because of that nice symmetry of the parabola. So it looks like m should be negative 2. So if I go back in here, all I have to change, I don't have to change what's in my table because I still want h to approach 0. All I need to do now is make this a negative 1 and this a negative 1. My table updates, and notice that it appears that my slopes are approaching negative 2. Isn't that kind of nice? So what you can do is you're doing your homework, you can kind of keep the same Desmos applet open, and you can just kind of tweak your functions and tweak the a value that you're trying to find. Is this making sense? Yeah? If you want to use your calculator, go for it. Use whatever you're comfortable with, but Desmos is really nice because then you can define the function and it just does a lot of the computational work for you, which is great. Okay, I feel like I've talked for a long time. I think I'm going to go ahead and skip example 2 here because we already did a different example with the negative 1. So just for the sake of time, I'm going to go ahead and skip that one here. I do have kind of an interesting application for us to look at, and I think I will have us go ahead and do that right now. Do you guys want to take a 5-minute break right now and then do this, or do you want to power through? I'm hearing both. Okay, I'll do a vote. 5-minute break right now? Okay, and power through? You can get more power through. Sorry, feel free to take a break if you need to, absolutely. I'm going to play a video. It's a physicist on YouTube. It's actually funny, his name is Mr. Anderson. Like, you know, The Matrix. Come on. And he's a physicist, and I really like the way that he talks about position, velocity, and acceleration. He already found one of them for us. That is the average velocity from 0 to 10. What did he say, 5.41? Is that right? 5.41 meters per second. And notice that that is slower than the average velocity that he calculated of like 10 something. And that makes sense, right? That Usain Bolt is going to start off kind of slower and then pick up speed as he's running. So that kind of makes sense. Do you have a question, Mason? Oh, is it not up right now? Thank you. It's hard to tell when it's behind me. Try again. I will try again. Now it's saying couldn't connect again. Yeah, that's so weird. I've never had this issue with this before. If this doesn't work, I'll switch to the doc cam. I will be disappointed.